Hello, my name is Martin Bloemendaal. Welcome to this lecture on sensible heat storage. The goal of this video is to provide you with a basic understanding of the working principles of different sensible heat storage technologies and their application in the energy transition. In the previous video, we concluded with this overview of sensible heat storage technology options, which include tanks and pits, abandoned mines and the underground. In this video, we will discuss these in more detail. Therefore, we will discuss the basic working principles of sensible heat storage, the characteristics of these heat storage technologies, and which factors affect their feasibility and successful application in practice. Let's start with tanks and pits. In this slide, you see some examples of how these tanks and pits look in practice. These specific examples are all connected to district heating networks. As you can see, they can be considerable in size, ranging from 5 to 50 terajoule respectively. For small-scale applications, storage tanks are used. For example, 300-liter tank connected to a solar collector can provide domestic hot tap water to an individual house. The basic idea of the tanks and pits is to insulate them to prevent heat conduction through the walls of the storage systems. They can be buried in the underground to take advantage of the stable soil temperature and the insulating capacity of the subsurface. In that case, it also allows using the space on top of the tank or pit for other purposes. However, burying them is relatively expensive compared to installing them at surface. Another important feature of tanks and pits is thermal stratification. During charging and discharging, the hydrodynamics inside the tanks or pits cause mixing and exergy loss. To prevent this from happening, inflow and outflow points at the top of the bottom are used to promote the thermal stratification. Due to the dependency of water density on temperature, the hot water with lower density remains in the top part of the tank and the colder, denser water at the bottom. The inflow and outflow points are often specially designed to inject and extract with little turbulence to prevent mixing. This is important because, like all sensible heat storage technology, the amount of thermal power output is defined by the flow rate and the volumetric heat capacity of the storage medium, together with the temperature difference between the supply and return. Maintaining this thermal stratification is key for ensuring a high heating power availability during discharging. I will now briefly discuss heat storage in abandoned and flooded mines and caverns. Their application potential is limited due to their limited presence in areas where we have need for heat storage. A key aspect related to storage in mines is the required seasonal storage volume in relation to the size of the mine galleries. Injecting a relatively small amount of heat in a much larger mine will be strongly diluted. Unlike the nice thermal stratification in tanks and pits, it's difficult to control the mixing in such systems, resulting in low extraction temperatures. From a more practical point of view, the debris in abandoned mines can be an important aspect to be considered because it may clog or damage pumps and heat exchangers. Also in caverns, it's difficult to control the thermal stratification, and often the chemical composition of the medium in the cavern is challenging to deal with. In spite of these challenges, if you have such system present at your site, they could prevent a major capital expense for creating heat storage, and therefore worth considering to use for heat storage. For example, in cities in former mining areas. Now, let's move on to the shallow subsurface heat storage options. We distinguish between the borehole heat exchangers and aquifer thermal energy storage systems. In the second week of this MOOC, the borehole heat exchanger system was presented to you to extract heat from the underground. But these systems can also be used for storage of heat. In summer, the house can be cooled and thereby storing heat in the underground. Instead of cooling the house, heat can also be stored from additional sources, like for example solar collectors. The big advantage of also using borehole heat exchangers for cooling or adding heat to the system in summer is that their length can be designed much shorter compared to if you were to only extract heat from it. Typically large heat storage system using borehole heat exchangers are clustering of many boreholes. The example on the slide shows the top view of such a system, where the boreholes are connected in such a way that the highest temperatures are in the middle of the borehole field and separated from the ambient subsurface temperature by the outer ones. This promotes the extraction of high temperatures when delivering heat from it. Now let's look at the last sensible heat storage of this video, Aquifer Thermal Energy Storage, or ATES. With typical ATES operations, during warm months, groundwater of a temperature of about 5 to 10 degrees Celsius is extracted from the cold well and pumped to the surface, where it will be directly used to cool the building. During this process, the water increases in temperature to about 15 to 18 degrees and it's simultaneously injected back into the aquifer into the warm well. When the cold weather starts, the flow direction is reversed and the water is pumped from the warm well to provide heating to the building, together with a heat pump, and again storing the cold groundwater from the evaporator of the heat pump for cooling purposes during the next warm season. To allow for the extraction and infiltration of groundwater, we need sandy layers, which are called aquifers. Water is extracted from an aquifer and pumped through a heat exchanger and subsequently re-injected into the other well. Please note that there is no net extraction of groundwater, only temperature change. The animations on the screen illustrate the changes in temperature distribution in the aquifer during winter operation. The warm water is extracted to heat the building, the groundwater becomes colder and is pumped back into the aquifer. The zone of cold groundwater increases and at the same time the volume of the warm groundwater shrinks. The opposite happens during summer. The radius of the volume affected by the temperature changes is about 50 to 150 meters and depends on the aquifer thickness and the storage volume required to provide the heating or cooling to the building. The distance between the wells must be large enough to prevent a negative interaction between the warm and the cold zones. These systems can also be made for large-scale seasonal storage, like tanks and pits, also at a higher temperature. However, this is not yet widely applied, but it can be and is safely done at several places around the world with a large potential because, like with mines and caverns, the heat storage does not require a large investment. And with the big difference that aquifers are widely present across the world. To summarize our learnings, we learned that various sensible heat storage systems exist, where tanks and pits can be customized to the required storage condition, but are relatively expensive to build and take up space. Mines and caverns potentially save a significant investment for heat storage, but they are not present in many cities and have some practical challenges. And lastly, the subsurface can be used. Relatively cheap to install and limited space use at the surface, but heat losses are less easily controlled. In the next lecture we will go into more detail regarding the phase change and thermochemical heat storage technologies. Thank you for your attention.